Hello everyone. In this video, we will learn about normalization. What is meant by normalization? Normalization is the process of organizing data in a database. Basically, it is used to minimize the redundancy from a relation. Also, it can be used to eliminate insertion anomaly, updation anomaly, and deletion anomalies. So in normalization, what it does is a bigger table, it will be dividing or decomposing into smaller tables, and then by means of this decomposition or the normalization, we can reduce the redundancy from the database. So basically, when we talk about this normalization, there are various normal forms present. One is first normal form, second normal form, third normal form, and all, because even fourth normal form, fifth normal form, BCNF and all are there. But the most commonly used normal form is the third normal form, that is considered to be the good enough for typical applications. So what is the first step is like you have to decide whether the given relation is in a good form. Relation means table. So this one, if R is not in good form, that means we have to decompose that into smaller relations. Suppose R is a relation, then we can decompose that R into a set of relations like R1, R2, etc. We can decompose into smaller relations, so that each this smaller relations will be in good form. So you should be very careful that when you are decomposing a relation R into R1, R2, etc., then that decomposition should be a lossless joint decomposition. That is lossless means when you join back these relations, you should get the original relation back. So basically this is based on functional dependency. So you need to understand what is meant by functional dependency also. So before that, let us see one example wherein I was talking about this deletion anomaly, updation anomaly, insertion anomaly. I'll just explain what exactly it is. So we have a table, a relation with the attributes. We can see that there are attributes: branch name, branch city, assets, customer name, loan number, and amount. So here in this, so there are 6 attributes here. You can see that. So here in this relation, you see that in branch name, we can see that downtown is there, then Redwood, then Perry Ridge, then again downtown is there. So branch city is Brooklyn, Palo Alto, Housneck, and Brooklyn. So here when you talk about this relation, you can see that this branch name is repeating. Even the customer name is there, and I suppose if when so this branch name is repeating, even the branch city is repeating. So basically wherever this new loan is being taken, then this branch name and branch city is getting repeated. So that is basically redundant data because it is repeated for each loan that a branch makes. So it wastes actually, the space is wasted. So now what we can talk about is like, suppose I'm talking about insertion. Okay, so now suppose I am just adding some name here. If I add some branch name into here, so a new branch name I am adding here into the table. But if I don't have any loan number or the customer name associated with that, then I'm not able to add a branch name here, because this all becomes this tuple. The remaining values become null. So that is called insertion anomaly. When we talk about deletion anomaly, suppose I'm deleting, for example, this Redwood, this Palo Alto. I'm just removing this customer name Smith. The loan is, I'm just removing this one. So basically, if I remove this tuple, the branch name and the branch city will get deleted along with this complete tuple. So then you won't be getting the information about that particular branch name. This is called as a deletion anomaly. Another thing which can occur is the updation anomaly. In this particular case, suppose I'm updating the value of asset, for example, for downtown. Instead of, I'm just updating this value. Uh, 90 lakhs. Just changing this value to 80 lakhs. So what is happening is, like, wherever this downtown branch name is occurring, I need to update everywhere. So suppose it is 1000 tuples are there where this downtown is appearing, all these places need to update. This is called as updation anomaly. So this is particular relation in which all these anomalies are present, because we can see that this is a bigger table in which 6 attributes are there. So basically, when we decompose this table into smaller tables, then we can get rid of this anomalies. So that is the purpose of normalization. The purpose of normalization is to eliminate redundancy or to get rid of this anomalies present. Now, how we can decompose? As I said, this complete table, we have 6 attributes here. That is branch name, branch city, assets, customer name, loan number, and amount. So this table or the relation can be decomposed into smaller table. So what can be done is, this branch schema, I can decompose this lending schema. Schema, you can see that 6 attributes are present there. This lending schema I can decompose into 2 schemas. One is branch schema, in which we have branch name, branch city, and asset. That means 3 attributes are present. And in the second relation, we can make it loan info schema, in which customer name, loan number, branch name, amount is been given. So when we decompose this the main table relation into the smaller schema, so what we have to do is, when we join this thing, basically when we are decomposing, for example, this is R1, this is R2, and the original one is R, then the all attributes of the original schema should be present when you take the union of these two schemas, these two new relations. So basically, the original schema R must appear in the decomposition R1 and R2. That is, R should be R1 union R2. R2. This R1 is the new relation and R2 is the new relation. So when you take the union of this two new relation, you should get the original relation. Then you can say that it is a lossless join decomposition. This is called a lossless join decomposition. Then another thing, when you need to understand when we talk about normalization, is functional dependency. That is, functional dependency is something that is a relationship that exists between two attributes. Okay, so usually it exists between a primary key and a non-key attribute within the table. For example, you have two attributes x and y. So if the representation is like this, that means that the value of y can be determined by knowing the value of x. That means if you know x, then you can determine y. So the left side of this relation is called determinant, and right side of this relation is called dependent. So left side is called determinant and right side is called dependent. So if this functional dependency is given like this, this means that y is functionally depending on x, or in other ways you can say that x determines y. So this is the functional dependency. For example, when we talk about an employee table, which has the attributes employee ID, employee name, and employee address. So as you know that employee ID is a primary key. So by knowing employee ID, you can easily find employee name. That means that employee name is depending on the attribute employee ID. So similarly, the employee address also. So this is how we can define functional dependency, because employee ID attribute can uniquely identify the employee name attribute from the employee table. So that means that if we know employee ID, then we can easily find employee name. So this is the functional dependency associated with that one. So you can see that left hand side we have put employee ID, that is a determinant, and right hand side we put employee name, which indicates that if we know employee ID, we can easily find employee name. You can say employee name is derived from employee ID. So employee name is basically fully functionally depending on employee ID. So another you can just see another example here. So basically it is a value that a set of attributes determine uniquely the value of another set of attribute. So basically if you have a functional dependency like this, B is depending on A, means that for every value of A there is a same value of B. So suppose here, for example, A values are 1, 2, 4, 1, 4. Suppose A value is 1, and when we know the value of A, that means that you can find B if this functional dependency is true. So when I know the value of A is 1, the value of B is 3 here. Now let us see in this particular column, again you have value of A in the fourth row, then you can see that the value of B is the same. So if it is functionally dependent means that value should hold. So but here A to B is true. But B to A is not true because if you have this value of 3, let us consider if you know the value of B, can we determine A? So now the value of B is 3. Okay, so the value of A is what? 1. So by knowing the value of 3, can you say that the value of A is 1? No, because in the second row you can see the same value of 3, the value of A is 2. So that means that the functional dependency B to A is false here. So here A to B is true. That means that for every value of A we can determine the value of B. But for every value of B you can't determine the value of A. So A to B is true but B to A is not true. So this is an example of functional dependency. I hope you understood what is this functional dependency. Now, if K is a super key for a relation schema, if and only if, see here, K is a super key, if and only if. What does this mean? This means that K is on left hand side means that is the determinant and R is depending on K. That means that by knowing the value of K, you can find R. So if you are able to find all the all the attributes of a relation R, then you can see this K is a super key. So another thing is, if when K is a super key, if you can determine all the attributes from this, the relation can be, all the attributes can be determined by knowing the value of that particular attribute. So another thing is, then you can say it is a super key, and if K is to be a candidate key, if and only if this should also hold, that is by knowing K, you can determine the attributes of R. Also, there shouldn't be any subset of K, subset in K, that is there shouldn't be any attribute which is a subset of K which can determine the relation, the complete relation. That is, there shouldn't be any alpha which is a subset of K such that alpha determines R. Then that means that is only if then that is not a candidate key. If no alpha, that is a subset of K. If there is no subset of K which can determine the relation, then that you can say it as a candidate key. There are various types of functional dependency. One is a trivial functional dependency. So you can say, see, when we are writing the functional dependency like this, B is functionally depending on A, or you can say A determines B. So how you can find this B from A? So this functional dependency is trivial if B is a subset of A. So if B is subset of B, A means B is included in A. So if B is a subset of A, then the functional dependency is trivial. So another one is A determines A, B determines B. B is functionally depending on B, because from knowing the value of B, you can determine B that itself. So that is also functional dependency. You can say trivial functional dependency. So here, for example, you have two columns, employee ID and employee name. So by knowing employee ID and employee name, so you can see here, this is a subset here, employee ID and employee name. So B, the right hand side is a subset of left hand side. You can see left hand side is employee ID and employee name. and right hand side is employee ID. So employee ID can be easily determined if you know the combination of employee ID and employee name, because already employee ID is present there. So this is a trivial functional dependency because it is a subset. Non-trivial functional dependency means if this one B is functionally dependent on A, or A determines B. This is a non-trivial functional dependency if there is no intersection. So it is B is not a subset of A. B is not a subset of A. Then you can say that it is a non-trivial functional dependency, or you can say if intersection of A and B is null, then the functional dependency A to B is called as complete non-trivial functional dependency. For example, ID. Left hand side is ID and name, right hand side is name. You can see that this one, ID and name, there is no intersection. So this is a non-trivial functional dependency. The name, date of birth. Another type of functional dependency is semi non-trivial functional dependency. So in semi non-trivial functional dependency, in that one, basically the intersection of x and y is not null, then it can be semi non-trivial functional dependency. For example, AB determines BC. So here this one is not actually, the intersection is not null. So here we can say that it is semi non-trivial functional dependency. Another thing you need to understand is the closure set of functional dependency, because this is very important, because the closure is like, it is a set of all functional dependencies which is implied by that functional dependency, that is closure of F. So generally we denote the closure of F by this denotation, that is F plus. So this is how we represent the closure of any attribute, and we can find the closure by means of Armstrong's axioms. What is this Armstrong's axiom? So the first one is, if beta is a subset of alpha, so then you can see beta is subset of alpha. That means beta is included in alpha. So that means that if you know alpha, you can easily determine beta. That is, if you know alpha, you can determine beta. So by knowing the value of alpha, you can find the value of beta. This property is called reflexivity. The another one is, if you know alpha is, if you know alpha, then you can determine beta. That is, if beta is depending on alpha, then if you are multiplying that alpha with another any variable, then that is gamma alpha determines gamma beta. This is called as augmentation. So if this functional dependency is true, holds, then you can say gamma alpha also determines this gamma beta. Another, this one is called augmentation. The third one is called if alpha determines beta and beta determines gamma, that means that by knowing alpha we can find the value of beta, and by knowing the value of beta we can find the value of gamma. What does it indicate? By knowing alpha we are finding beta, and by knowing beta we are finding gamma. So indirectly you can say that by knowing alpha we can find gamma. So that is what, by knowing the value of alpha we can find the value of gamma. So this property is called transitivity property. So these are Armstrong's axioms. So some more axioms are there for the computation of closure, functional dependency closure. We find this another functional dependency, that is, if alpha determines a beta, this one is that if we can determine beta by knowing the value of alpha, and you can determine another value gamma by knowing the value of alpha, then alpha can determine beta gamma. So the right hand side of here is beta, here the right hand side is gamma. So this property is called union property. So if alpha determines beta and alpha determines gamma, then alpha determines beta gamma. Another one property is called decomposition, that you already have alpha. If alpha can determine a combination beta gamma, then you can separate this one, that is alpha can determine beta and alpha can determine alpha gamma. So if alpha determines beta gamma, then if that is true, then alpha can determine beta and alpha can determine gamma. So this property is called decomposition. Another one is called pseudo transitivity. That is, if alpha determines beta and gamma beta determines delta, then alpha gamma can determine delta. So these are all called as Armstrong's axioms. So we may be using this while forming this functional dependency attribute closure. So let us see one example to find attribute set closure. So let us have an example here. So R is a relation and A, B, C, G, H, I are the attributes of this relation. So attributes means it is a column heading, you know. Then A, B, C, G, H, and we have this following functional dependency. What are this functional dependency? We have first functional dependency that by knowing A, we can determine B. So B is functionally depending on A. Second functional dependency, C is depending on A. Then we have H is depending on CG. I is depending on CG. H is depending on B. Let us see, let us find the closure of AG. So we have taken a set functional dependency attribute set AG and finding the closure of this one. So when you are finding the attribute closure, the first thing you have to do is, suppose you are finding the attribute closure for this one AG, then the first element will be AG itself. Okay, when you are finding the closure, the first element will be that itself. So AG closure, the first element will be AG. Now what we have to do is, in this AG, what all attributes are present. So we can see A is present and G is present. Now you just observe this functional dependencies. Now observe this functional dependencies. First one, let us take A. So when you observe the functional dependency, you just check whether A is there present on left hand side. Yes, you can see A is determining B and A is determining C. So from this we can see that by knowing the value of A, you can find B and C. So our closure now, the first one is AG. So we can include BC also, because you know A, and now by knowing A we can find B and C also. So in the closure set you put B and C. So now our new closure is A, B, C, G. So this is our new closure. Now let us see this attributes over this functional dependency. A to B we have already found, A to C we already found. Now let us see the CG. So CG can determine H. Also CG can determine I. So now our attribute closure becomes A, B, C, G, H and also I. So A, B, C, G, H and I. So now B can determine H. So H is already included in the set. So we don't have to include it again. So now this is our final set, that is A, B, C, G, H, I. So when you see the final result A, B, C, G, H, I, you just see the relation. What was our original relation? It was A, B, C, G, H, I. So we were having all the 6 attributes, and AG closure we got the same set. That is, we could find the relation R by finding the closure of AG. So what does it mean? Is AG a candidate key? So before finding whether AG is a candidate key, we need to find whether AG is a super key. So what is the definition of super key? Super key, if you can get if all the attributes in a relation can be determined by knowing that particular attribute, then you can say that is a super key. So here by knowing AG, we can find all the attributes in the relation. So what is this AG? AG is a super key. So AG is a super key. Why it is a super key? Because we can find all the attributes. We can determine the complete relation by knowing AG. So that is a super key. Now you have a super key, and what is the definition of candidate key? Candidate key means the subset of the super key shouldn't, none of the subsets should determine the relation R. So the complete relation shouldn't be determined by the subset of this one. So none of the subsets should determine that one. Then you can say that is a candidate key. So now let us consider this A, whether A can determine R. So whether A is a superset of this R, then you can say. So A is, by knowing A, we can't determine the complete set. So there is no subset which can determine the no subset ni. It is like A, the subset A can't determine the complete relation R. Now let us see the second subset G. So by knowing G, can we determine the complete relation R? No. If you take the closure of G, you are not getting the complete relation. So A and G, there are no subset which can completely determine this relation. That means that this is a candidate key. So this is how you find super key and candidate key. Candidate key means the subset of the super key shouldn't there shouldn't be any subset which can determine the complete relation. That is the candidate key. What is the purpose of why we are finding this attribute closure? So one purpose, there are several uses. Main purpose is for testing for super key. So how will you test for super key? Just now I have shown you. So you will be taking an attribute, then you will be finding the closure. So when you can find, if that particular closure contains all attributes of R, then you can say that is a super key. So for testing the super key, you can use attribute closure. Also you can test functional dependencies, if you want to check whether this alpha can determine beta, whether this functional dependency hold, whether it is in the closure, we just need to check whether this beta is a subset of this closure of alpha. So first you find the closure of alpha, and if beta is a subset of alpha closure, then you can say that it is this alpha to beta holds. That is, you can check, that is, you have to compute the closure of that particular attribute and check whether the right hand side attribute is present there. So that is a very easy method to check whether that is functional dependency holds or not. So this is the thing for now. Finding candidate key and super keys using attribute closure, I already explained. That is, if an attribute closure of an attribute set contains all attributes of a relation, then that attribute set we call it as a super key. Otherwise, if no subset of this attribute set can functionally determine all attributes of the relation, then you can say that is also a candidate key. So this is how you will be finding candidate key and super keys using attribute closure. It is very easy method, and I suppose you understood how to find attribute closure. Attribute closure is like you take the attribute, then find the functional dependencies and check out all the dependent how it is coming. Then coming on to the normal forms, as you know, we were talking about the normalization, and as you know, the database community has developed various guidelines for normalization of the database. So these are referred to as normal forms, and they are numbered from the lowest form of normalization is called first normal form, or in short you call it as 1NF, and it will go through fifth normal form 5NF. And basically, if you see in practical application, we have 1NF, 2NF and 3NF, and sometimes occasionally 4NF also will be there, and fifth normal form is something which is rarely seen. And I'll just briefly explain what is this various normal forms. And this first normal form, second normal form, third normal form, then Boy's Codd normal form. These are the various types of normal forms we have. And in first normal form, it states that a relation is to be in first normal form if it contains atomic value. Atomic value means there is no multiple values, it should be atomic in nature. So second normal form, a relation is said to be in second normal form. First condition is that relation should be in first normal form. And second thing is, all non-key attributes are fully functionally dependent on primary key. Now you know what is the functional dependency. So for understanding this, I just mentioned what is a functional dependency. So we can see that all non-key attributes are fully functional dependent on primary key. Third normal form, the condition is that it should be in second normal form and there shouldn't be any transition dependency. Fourth normal form is that it should be in Boycott normal form and there shouldn't be any multi-value dependency. Fifth normal form means that should be in fourth normal form and it shouldn't contain any joint dependency and joining should be lossless. So with this, I have given an introduction to normalization. I will explain about the various types of normal forms in the upcoming video. Hope you understood what is meant by normalization, and thanks for watching. Thank you.